Good morning. Good morning, students. Okay, two things to inform before I start. So first about the assignment. Okay, so the assignment, as you put, I mean, if you look at the scope of work, supposed to release last week, but the assignment is based on your chapter 3. So that's why, okay, I hold so that you have time later. Okay, so to so if I release, then you have a shorter 1 week. Okay, so I mean the duration. So when I release this week, so then once next week when we start off with your chapter 3, which is the thermodynamics. So because your assignment will base on designing an experiment, okay, based on your gas law, which is the gas laws which you learn in your chapter 3. So Friday, it will be in your Moodle. Okay, so you can check all the details. And then I also have updated the for the students who does not have a group. Okay, so I have that one I have updated in the Teams. All the students would have actually seen. So those students which is in the group I have set, because that's the only group that's going to be a mix between physical science 3 and the the other class. Okay, because I'm not able to form a group within that class, so no choice, because it's like 1, 2 from different class. So I joined them. Okay, so into a group. Okay, but that group has 5 members. That's the only group have 5 members. Okay, so I did not get any. So those students who some I think not here the student. Okay, so not here. So I'm not sure whether still continuing in the program. So I need to check with the office. Okay, so I did not get any update from the student. Okay, so but then from based on the name list I have, so the students who does not have a group, okay, already formed into a group. So the others already have a group. Okay, so you can roughly make an idea. Okay, so the assignment is going to be based on a gas law. So you have choice of choosing any of the gas law between the three gas laws when we discussed during the practical. Okay, so you need to come up with a way to demonstrate that law relation. Okay, so with a simple apparatus within the lab that you can find. Okay, so to demonstrate, mean we can do a demonstration. So we are not going to do the experiment in front. Okay, so but then you can do it your own. Okay, so then you can attach the picture of the setup arrangement. You can add a real picture in it together with the drawn setup. Okay, so label. So you will see that in the detailed instruction. So further, okay, so if you anything that is need to clarify, okay, so then you can ask me, okay, so in Teams, then I will have collect the whatever questions that's posted. Then next week I will address the whatever questions that has been posted. Okay, so in case if you are not clear of the assignment, okay, so that is one. So another thing I need to mention is on the week 9, okay, so Friday, okay, so I will be on leave. Okay, so therefore that's week 9. Okay, so later that is in June 7th. Okay, I'm just informing. I mean, this is what based on the plan. Okay, something emergency, I don't know. Okay, so but this is I already have a occasion, a function, okay, to attend, which is I have to go to the northern part of Malaysia. Okay, so therefore definitely I will not able to uh, have the class. So I will later I will discuss about the arrangement for the replacement time. Okay, so this informing. Okay, so I think on 7th, it is Friday, 7th of June, Friday. Okay, so my lessons, there will be no lessons. So we will ultimately look into to replace. Okay, that's the two announcement. Any questions? Any questions from the floor? From the floor. Okay. Any questions from students? No, okay. So I hope you are working with the chapter one. Okay, so I mean the tutorial session has been going. Okay, so I hope you have uh, asked questions that you had problem. Okay, and clarify during the tutorial. So once this is tutorial once is completed. Okay, so and then I will roughly I will share a guidance answer solution, but it will be a my handwritten scan. So I will share to you all. So you can have that will actually guide you. Okay, so in your tutorial questions. Okay, so for the chapter one, and gradually I will do it for the other chapters as the tutorial section goes. Okay, so I mean next week. Okay, so after the chapter 2. Okay, so but then our tutorial is week 6. So then I will also share for the chapter 2 and so on. Because I don't think so with 4 sessions of tutorial, we are able to cover lot the most of the questions in the tutorial. Only we can emphasize to look into the difficult one. The basics one, I'm very sure some students may encounter problem with the some basic questions. You may need some further assistance to understand to solve the problem. So that I understand that. So I give you a written form because this is as mentioned, so order whereby we are not supposed to give you a full work solution. Okay, so because we want the students to attempt, work, and come for the tutorial. Okay, so request and ask. But then because this is uh, don't much time of tutorial we can spend. So I think, I mean, it's additional work for me. Okay, so I will write down. Okay, so some guidance of the how to solve. Okay, and I will share that. Okay, to the uh, I will share direct to the then it can be shared to the class group. So that is actually in the form of so that I will help you. And anything further I have addressed. Okay, so then see as progress I will try to give a short video explanation on certain things if I got to know that students having problem on certain areas. So as we go. So see, the first 5 weeks is going to be very tight for us, okay, so lecturers, because there's a lot of things that have to be prepared, especially for your final exam papers and so on. That's why we could not really look into the other matters. Okay, so that's it. So we'll move on to the lesson. Okay, no question, huh? So continue with the interference concept. Excuse me. We did talk about the optical path difference, optical path length. So in fact, the optical path length, okay, so what we have seen earlier, okay, so that is just an intro. The more specific where you need to know for your exam purpose is here. Okay, so start from here because this is what you are going to apply into interference, finding whether it's a constructive interference or destructive interference. So look at this the point here. Okay, that's my pen. Okay, so interference concept, optical path difference. So when you say optical path difference, so meaning as I think I did mention about the difference. Okay, for example, I use the example if you want to exit from the door one here and the door two. Okay, so definitely the distance for me to travel to this door and that door is different. So therefore, if I find the difference in the distance, okay, so I'm walking towards that door and that door, that actually gives us the optical path difference. You can see here when the path length are equal, so the waves are in phase and undergoing a constructive interference at P. So I think this particular slide I did mention we discussed the day, isn't it? Did we? Okay, so never mind. Just to recap. So away from the point S1 and S2, so it travels to point P. Okay, so when it travels to point P, but point meaning the distance from S1 to P and S2 to P will be the same. So if I take S1P minus S2P, it will definitely going to give me a 0. So the optical path difference is 0. Okay, now when you see it here, from S1 to P, there is the wave. You can see the wave. So how many wavelengths are there? How many wavelengths are there from S1 to P? So you can calculate. So this is considered as 1, 2, 3, 4, 5, and 6 lambda. Correct? 6 lambda. 1, 2, 3, 4. Oh, no. 5.5. Okay, it is like a 5.5. Those who mean, I'm very sure it's difficult for you to see. Okay, so on the board. Okay, so I mean here, but you can see from your TV screen. I'm not sure how is that. Hold on. Yeah. So you can basically see. Okay, so there is 5.5 right? Okay, so it's basically like you are looking at one complete cycle. So you calculate how many complete cycles are there. So you have 5.5. So that is from S1 to P. Then from S2 to P, also you have 1, 2, 3, 4, 5.5. Meaning, finally, when it reaches to the point P, okay, so 5.5. So the part difference, if you take 5.5 minus 5.5, it gives you 0. And look at the end here. When it comes to the end point, so this is going to give you a maximum output, constructive interference. So for the center one, exactly at the midpoint, the center bright fringe, okay, the center point. So you have a constructive interference occurring because the optical part difference is equivalent to 0. So meaning that it will either crest meet with a crest or throw meet with a throw. Even throw meet with a throw, it is a negative, but still is negative is a positive intensity. Okay, a positive, it is a maximum intensity. So a throw plus with a throw, it will give you a maximum also. Okay, crest meet with a crest also will give you a maximum. Only when crest meet with a throw, a positive plus a negative, then it will give you a 0. So that is the outcome for the destructive interference. You will see later. Okay, so see the part. Okay, so this one I can take it as L1, and this one is a L2, and then it is been drawn here. So it's like 1, 2, 3, 4, 5, 6.5. Here got 6.5, didn't matter. So if I have 6.5 lambda, here also 6.5 lambda. So the optical part difference will be equivalent to 0. So but we can see that if just say this is the direction where the wave is traveling, at the end we can see a crest meet with a crest will give you a maximum. Okay. So that is condition for a constructive to take place when the two waves are meeting at the midpoint. Okay. What happens to the other conditions? So now, see, when the path length differs by a wavelength, okay, or it can be a multiple of a wavelength. Okay, so 1 lambda, 2 lambda, 3 lambda, 4 lambda. Okay, what that will lead to? What are you going to expect? Okay, the outcome. So example, you can see S1 travels a further distance to point Q compared to S2. So what is the part difference here? S1 to P. So you count number of wavelength. 1, 2, 3, 4, 5, 6. Okay, so 7.5. Okay, so you get 7, correct now? Okay, 1, 2, 3, 4, 5, 6, oh sorry, 6.5. Okay, so you have 6.5. Then what about the S2 to Q? 1, 2, because always you must understand that one complete cycle means this is considered as one complete cycle, which will give you 1 lambda. So that's how, what I count. So 1, 2, 3, 4, 5.5. Just now was what? 1, 2, 3, 4, 5, 6.5. So 1, I have 6.5 lambda and 5.5 lambda. So when 6.5 minus 5.5, I get 1 lambda. Correct? So meaning the optical part difference is 1 lambda. So look at the explanation here. So if there is a optical part difference of equivalent to a lambda, then again you can see what is going to end up. So you have a crest going to overlap with a crest. So you get a maximum. So if the optical part difference is 2 lambda, if it is 2 lambda mean it's going to be here. So because this will be 2 lambda, again crest with a crest. If it is 3 lambda, okay, again crest to a crest. So you can notice that every time when the optical part difference is equivalent to a multiple of a lambda, that will lead to a constructive interference to take place. So you have a general order for constructive interference to happen. Okay, so which will be always in the multiple of a wavelength. So that will further lead to a conclusion. Understand that? Okay. So that is for constructive. So remember, so whenever the optical part difference is equivalent to a lambda, that is already explaining a case of constructive interference have occurred at that particular point. And that's what causes the bright fringes. So you did the experiment, okay, so on the diffraction, okay, so and then you observe, I mean double slit and also the multiple slit, and you have observed the fringes. So whenever you see the bright fringe, okay, so the center, 0 order, first order, second order, third order, fourth order, so on, that is the formation of that bright fringes are due to the optical part difference is equivalent to multiple of lambda. The one exactly at the center, optical part difference is 0. The first order optical part difference is 1 lambda. Second order, 2 lambdas. Third order, 3 lambda. It goes on like that. Okay. So that's for the constructive. Move on. For destructive. So if it is for destructive, then obviously we are expecting they cannot be in phase. Okay, so it cannot be crest and crest, throw and throw. It has to be one crest and one throw. If it is one is going to be a crest, another one is going to be a throw, surely the optical part difference has to be equivalent to half lambda, cannot be 1 lambda. Okay, so it has to be always in a fraction of a half lambda. So you have half lambda, 3 over 2 lambda, 5 over 2 lambda. So I mean, one half lambda, 1.5, 2.5, 3.5, 4.5. Always you will have a half there. Because whenever you have the half mean, one is crest, one is throw. So it is going to give you a destructive interference. Okay, now you look at it. So when the path length differs by a half wavelength, which is 180 degrees, which we understand as the half of phase, it will undergo a destructive interference. So S1 to point R, S2 to point R, you may count 1, 2, 3, 4, 5, 6. So I have 6 lambda here. Then 1, 2, 3, 4, 5.5 lambda. So therefore, when you find the difference, this will be half lambda. So half lambda, look at the end here. Okay, so when you go to the end, okay, so oh sorry, I'm supposed to take this end. So here you see crash and throw. So crash and throw going to cancel off each other. If their amplitude is exactly same, okay, so S1 and S2. If the S1 and S2 is a coherent source, and originally it comes from the same single source, but it is been diffracted by a double slit, then we are expecting the amplitude to be same. Okay, approximately the same. So definitely the amplitude is same in if one is positive A, another one is a negative A, definitely is going to cancel off, will give you a zero output for the constructive. The outcome for the destructive, this is a condition. The outcome for the destructive to be zero, okay, basic condition mean they must be out of phase. There must be a phase difference, which is in the fraction of a lambda. Okay, but then that is not the ultimate condition for total destructive. In order for a total destructive to take place, the both waves must have same amplitude. Only then, if one is positive A, another one is a negative A, they can cancel off. Otherwise, destructive happen, but it cannot be a total destructive. Okay, I think I did show before. If one wave is like this, the other one. So if this is positive A and this is a negative A, yes, the final outcome here, I can get zero. Because they will exactly when they meet at the point. And these two waves, okay, when they travel in the opposite direction and overlap each other. Okay, so one is moving to the right, the other one is moving to the left. So when they come together, when they overlap, okay, so it can cancel off. Okay, this is actually a superposition. So the same thing over there. When this and this meets at a particular point, they will cancel off. Okay, but over here you can get a total destructive interference. You can get a total destructive interference. But if this is 2A, okay, or maybe just leave it as A lah. Okay, the other one minus half A. So if they are going to meet, yes, I still get destructive. It is going to be destructive, but the destructive here will be, I still have an amplitude of A. Okay, so amplitude of, sorry, not A, half A. Okay, so so the destructive happen, but then it is not cancel off totally. So in order for the cancellation total destructive to occur, the condition is both must have the same amplitude. In this case, okay, so we assume it's the coherent source, okay, coming from the same single source. So coherent source, they must have constant phase difference followed by approximately the same amplitude. Okay, so you have the outcome. So like earlier, okay, so for earlier, when you look at it, sorry, so we don't look at the front here. We are basically looking at the back. So you can see here, a crash meet with a crash. Okay, so a crash meet with a crash will give you a constructive, even though there is a part difference of 1 lambda. But when the path difference becomes half lambda, then when they overlap, so one will be a crest, another one will be a throw. So they will cancel off. Excuse me. What about the, did I pick out the batteries of the, to be out in the staff room? Okay, so the battery is around. Okay, so now we can see a general pattern here. So a general pattern for the optical part difference for the constructive and a destructive interference. So just now we have mentioned, okay, so for the part difference, you can see below the optical part difference, it is equivalent to 0, 1 lambda, 2 lambda, 3 lambda, and so on. So that is the optical part difference for the constructive interference to occur. Okay. So 0 mean at the center. Then you have 1 lambda, 2 lambda, 3 lambda. That is optical part difference. A general formula to represent that is m lambda. Okay, and sometimes you will see in certain books. Okay, so advanced book, it is written as n lambda. So it doesn't matter. So the m is referring to the multiple of the lambda. So m value can be either 0, 1, 2, or 4. Okay, so it's basically like multiple integer. Okay, so 1 lambda, 2 lambda, 3 lambda, 4 lambda, and so on. Okay, that is optical part difference. From optical part difference, we can move on to phase difference. Optical part difference will give you in term of lambda, or in fact, it is in term of the length. Okay, but phase difference will give you in term of angle in specific. Okay, so it can be degrees or it can be in radians. For example, say when the optical part difference is 0, the phase difference also will be 0 lah. They are in phase. Well, when the optical part difference is equivalent to 1 lambda, that means 1 complete cycle, which is equivalent to 2 pi. If it is 2 lambda, 4 pi, 3 lambda, 6 pi, and so on. Okay, so it is matter of what is the unit we use. Optical part difference is based on the length, and we will give in the order of a multiple of a lambda. Phase difference, we will give it in terms of angle, okay, so or in the form of radian. Usually, we will just refer to radian. So, and the general formula is 2 pi m. So, m can be 0, 1, 2, 3, and so on. So, if you substitute inside, when m equals to 0, the center order, okay, so then the whole thing is 0. But when m equals to 1, then you get 2 pi. M equals to 2, you get 4 pi, and so on. Any questions for the condition for constructive interference? Okay, huh? So, this will be a condition for destructive interference to take place. So, the key thing that you must remember for constructive, it is multiple of lambda. You don't memorize the formula. I won't advise you to memorize m lambda. Okay, 2 pi m. Don't memorize the formula. Okay, you remember in order for constructive interference to take place, the optical part difference must be in the multiple of a lambda. And for destructive interference, the optical part difference will be in a fraction of a lambda, half lambda, 3 over 2 lambda, 5 over 2 lambda, and so on. Okay, so because once you're able to remember the optical part difference, then I can figure out the phase difference. So if it's half lambda, then the phase difference will be pi, because half lambda is 180 degrees. 1 lambda is 360 degrees, correct? So half lambda mean it is 180. So pi. So if it is 3 over 2 lambda, then when you try to convert, okay, so you get 3 pi. Okay, so 5 over 2 lambda becomes 5 pi. Okay, so and so on. Okay, so that will give you a order. No need to worry to remember this formula. Okay, I will not advise, because there is much more easier way for you to recall. Constructive interference, the part difference must be in multiple of a lambda. Destructive must be in a fraction of a lambda. So that's it. Then the other things you can actually figure out. Okay, 1 lambda mean is the phase difference is equivalent to 2 pi. If it is half lambda mean the phase difference equals to pi. Okay. Okay, so could you try this question? The meantime, okay, so I just need to go and take the charger and come. Okay. So what is the answer? Two light rays of a wavelength 600 nanometer meet at a point. So find the three smallest optical part difference between the two rays for constructive interference to take place at a point. Yeah? What's the answer? Okay.
开始连接话筒，已解锁，请取出话筒。
Zero, 600. Okay, so we want find the three smallest OPD. Okay, so between the two rays. So three smallest. Okay, so one is 0. Then you have the 0, 1 lambda, and also 2 lambda, right? Okay, so that will be 600 and 1200. What about if I change that to destructive interference? It is destructive interference. The same question. Okay, so but then okay, so find the three smallest OPD between the two rays for destructive interference to take place. Yeah. The first smallest is this half lambda, so it is 300. Okay, then next one is 3 over 2 lambda. Okay, so then 3 over 2 times 600. So you have what? 900. Correct? Okay, so then you will have the next one 5 over 2 lambda. Okay, so 5 times 300. Okay, so you have 1005. Okay, so this is how it goes. Okay, a simple question, just we can play around with the constructive interference, destructive interference. And it will depend on the wavelength that is being used. Okay, so So this is double slit. Next example. Okay, now we are moving into double slit. Okay, so you have done the experiment about the double slit. Okay, so but then we can have many type of double slit based on the spacing. So double slit interference, it is also known as Young's double slit experiment. So the objective of this Young's double slit experiment or the double slit interference experiment is to determine the wavelength of an unknown source. That is what you have actually done during the experiment that we have conducted. Okay, to determine the wavelength of the unknown source. Okay, so I mean unknown light source. Lah. So we can use that to work for other waves, but then the observation for other waves is not that clear, and there is a limitation of getting the values. For example, if you want to find the wavelength of a water wave or sound wave, then like sound wave, you need to use a microphone to detect high pitch, low pitch. So it is a bit difficult. Okay, so you need to use more instruments which is more sensitive, micrometer connected to a cathode ray oscilloscope to give you the pulse of the sound that is detected and so on. Okay, so therefore the experiment Young's double slit is specifically referring to a light wave. Okay, double slit interference can be a general double slit experiment. It can be a general referring to different wave. But when we say Young's double slit experiment, meaning, okay, so Young only have used to that is referring to the light wave. So therefore, Young, when you use a Young's double slit, we are referring to a light wave. Okay, so this is the probably what is the outcome that you have actually obtained during the experiment when you did. Okay, so for practical 2. So you have a light source. Hopefully it's not too. Okay, so you have a light source. We have a incident laser beam directed to the double slit. I did perhaps mention during the practical session, a doctor would have mentioned, we don't really use a normal light bulb. Okay, so we use a laser beam, laser light, or even though if we use a light bulb, okay, so we try to use a lens, okay, so which is the convex lens. We use a convex lens to focus the ray, so we can have a very narrow beam of light when it arrives at the double slit. So then only the diffraction will be more obvious, because when you use a laser beam of light, laser beam are very intense source. Okay, so it is a narrow beam. At the same time, it is a intense. It has a very intense uh, energy. That's why, okay, laser light is dangerous. Okay, so especially when it hits our eye, because the intensity of the uh, intensity is actually amount of power, okay, per unit area. So meaning the amount of power per unit area of that laser is much higher compared to normal light. When you look at normal, you can see the normal light source, no problem. Because the intensity is being dispersed to bigger area. So meaning the amount of power that arrives per unit area is lesser. But when you use laser light, the amount is higher. Okay. So therefore, what happens is, moment it hits the spot, okay, so it is high enough to cause a particular cell. Hot and cold. Our eye will have a cell. Those who do bio will know that. Okay, long time. I did my bio when I did my form 6. Okay. So after that, okay, so but I feel there's something like a rod and bone cell in our eye. So these cells can be killed. The moment the cell is killed, then gone, so blind. Okay, so and when it hits our uh, direct to the point, okay, so then it will go and affect our retina. which is at the back of our eye. Okay, so put it aside. So that's the thing. Okay, so narrow beam of light. But then for the experiment purpose, this will able to give us a very clear bright fringe. If you use a normal light source, okay, bulb, the intensity of the fringes that you observe will not be clear. So now look at the observation. So when you look at the observation, so it's not according to a scale, didn't matter. So the distance to the screen is actually much greater than the distance between the slit. Okay, so meaning there's a distance between the double slit to the screen. Okay, so should be, it will be much greater. Usually it will be in the range about 50 cm. Okay, so less than 100 cm lah. It cannot be too far. If it is too far, okay, so it's going to affect. But then for double slit, it is quite, the distance is quite controlled. Cannot be too far. Okay, so because then again the intensity of the light will be lesser when it reaches to the screen. So then when you look at the point that is indicated here, so the two waves overlap as they spread out behind the two slit. So when the light of source from, okay, when it moves to the double slit, it experiences a diffraction, and the diffraction of these two waves produces two new sources, and these two new sources will overlap each other, superposition each other, which leads to a interference effect. So that interference effect, so to overlapping is also superposition. Overlapping is also known as superposition. This is example of superposition. Waves are overlapping each other. Two waves are overlapping each other. It is a superposition. Okay. So two waves overlap. Okay. So waves interfere, resulting in a pattern of light and dark bands on the screen. So you will see a bright and also dark band on the screen. Okay. So that's what you observe. And you can see, since if I ask you, okay, sorry, if you look at this pattern, is the pattern that you see is regular? Is the pattern is regular? Regular in the sense, meaning the bright fringe and dark fringe are spaced equally. No, no. Is that? No. For me, it looks like quite regular. See, maybe, okay, so I mean, see, it has to be regular, okay, because the two waves that you are using is a coherent wave, coherent source. So they have a same wavelength. So the pattern that you get must have a regular pattern, but maybe the width of the bright fringe and the dark fringe may not be the same width. But if you measure from the, okay, for example, see, if I measure from the center of the bright to the center of the other bright to the center of the next one, that distance must be same. The center, from the center to the center of the next fringe, that interval must be same, because that is the idea of coherent source. When that's why the condition is, in order to get a interval, okay, so an equal interval, a uniform distribution, so the two source that we use must be a coherent source. So if it is not coherent, we will not able to get a fringes. Okay, so a uniform pattern. Okay, so one may be thicker, one will be shorter. Okay, so because it depends on how they overlap. Okay, so when the waves are coherent wave, so the phase difference is constant. So we are expecting the intervals to be the same. Okay. Okay. Uh, you need to take a break. Okay. Sorry. I went just now, so I was thinking that is Okay, okay. So no problem. Okay, so take a break. Okay, so now it's 9:56. Great. Meantime, you can just have a look at this. Sorry. Okay, that's the time here. Okay, so I'm supposed to attend some a seminar speech. Okay, so that's my PhD course. Okay, so later after the class, I will go and join. Okay, so next. So double slit, we can see further from just now when you see it from the side. So this is a top view. When you look at the, hopefully they don't hear my lecture here. Okay, accidentally if I, okay, so uh, unmute my mic, then they will be hearing my lecture. Okay, so so here you have two. Originally, the wave is coming from a single source. When it arrives at the double slit, so diffraction takes place, and the diffraction produces two new sources. These two new sources, okay, so will overlap each other when they travel in the medium, okay, in a particular medium. When they travel, in the same direction, they will overlap. Okay, so that will lead to a constructive and destructive interference, as we discussed just now. So when there is a part difference of in order of a multiple of lambda, you have a constructive, and if it is a fraction of a lambda, you have a destructive. That is what observed. So we can see the zero order, which is the center maximum, first order, second order, third order, fourth order, and so on the side. Okay, so you will have on the both side. Okay, so which is on your left hand side and also on your right hand side. Okay, so but the orders are basically same lah. Zero order center followed by first order, second order, third order, and goes on. The maximum number of order can be observed on the screen. It is dependent on certain factors. Okay, so we'll look into that. So factors like the slit separation, which is the separation between the double slit here, this slit separation, the wavelength that we use, that also contributes to the number of fringes you are able to observe on the screen. Wait, just log out first from the session. Okay. So over here we can see maximum of 4 orders. Okay, so we can have more, as I mentioned, depending on the slit separation. Okay, so the wavelength that we use, the distance between the double slit to the screen, and in fact the length of the the length of the screen to see number of orders. Okay, but the length of the screen will not be included in the formula. Okay, because that one is not a factor that is going to change the fringe separation that is observed on the screen. Okay, then when you look at the pattern of the fringes that is observed, do you see any kind of difference to explain? This one is your observation. I'm asking you. When you look at the pattern, do you observe any difference in the pattern that you see? Yeah. Do you see any difference? What is the difference that you see? If you look at the center, it appears to be brighter compared to the end, correct? Okay. So the center fringe will be brighter, obviously. Why? Why center fringe is brighter than the fringe? Okay, so the fringes which is away from the center. Okay. I have two people to ask that question coming forward. But I'm being also listening. Okay, now. Yeah, sure. So give me so if you look at the fringe, okay, so the center fringe appears to be brighter compared to the order fourth, the fourth order. It's any fine. Means having okay. Your friend can right? I know. Why the center, the zero order will be much brighter than the, especially we can see the difference in the third order and the fourth order. Yeah. It's small. Okay. Like this. Okay, so yeah, so it's pretty small. So in a way, when you say it's pretty small, it is you're looking at the distance it travels. So when it travels, thank you. So when it travels to center, the path it actually moves. When you look at the path, then it moves, it appears to be shorter. So sorry, if I show it over there, so this student here. Okay, so if you look at the path when it travels to the center, this distance is appear to be shorter. So there is a formula which explains about intensity of the light is inversely proportional to the distance square. Okay, so this is you learn in your waves, I think. Those who did the waves and mechanics and waves, you all did mechanics and wave? No, what isn't it? Mechanics and wave. Oh, okay. So many, I also don't know. Okay, so which track? Okay, so in mechanics and wave, so you have when you discuss about wave in specific. So intensity of the light is intensity I mentioned just now is the power that is arriving normally per unit area. So intensity is inversely proportional to the distance square. Okay, so meaning okay, obviously if I stand here and I speak, it's all not using the mic. Those who over here can able to hear compared to the one at the end. Because the distance the energy is going to travel is further. So as the further it travels, there will be a decrease in the amount of power that is being transferred across. Okay, so the same thing. So when the light travels a further distance over here, so it is being stretched further out. So the distance it moves is actually further. So therefore the intensity of the light will be less. That's why it appears to be less brighter. It's a bit dimmer. Okay, but still it is a constructive. Okay, the constructive interference takes place. But because the distance it moves, that's why it appears to be dimmer. Okay, other than that, okay, so it is not because of the overlapping of due to the overlapping waves, something changes and so on. No, okay. So when they overlap, okay, so same condition, okay, so you have your uh, the optical part difference, okay, so there will be a difference in the order of a lambda. Okay, any questions on this? Okay, so look at the point. Okay, so the first point indicates a plane wave is incident on a double slit. A plane wave. Okay, so a plane wave it can be also referred to a water wave, or we can also refer to a light source. Then, sorry, where's second point? Second point, waves spread out behind each slit after the diffraction. So diffraction have happened. Third, constructive interference occurs when R1 and R2 differ by a whole number of wavelength, multiple of a wavelength. And fourth, destructive interference, that is the dark fringe. Destructive interference occurs when the R1 and R1 and R2 differ by a whole number of wavelength plus half lambda, meaning it is a fraction of a lambda. Okay. So this is the same thing, but this gives you more information about specific points when they overlap. So we have the points known as node and antinode. I'm not sure you have learned that. That should be a part that you have covered in your SPM or in your IGCSE. So every point on a wave, okay, so when two waves overlap, okay, so when crest and a crest, throw and a throw overlaps, that particular point we call it as an antinode. So if you look at this, whenever you get a maximum, okay, when you get maximum, it is because you can see the red dots. So these are the points whereby a crest and a crest overlap. In between, I mean, it is not drawn here, like in between didn't show, but in between you must understand there must be a crest and a so throw and a throw. So when throw and a throw meets also will give you a constructive. Crash and a crash meet also will give you a constructive. So you need to see that. So for example, okay, so I can also label that as blue point. So the blue point in between is where the throw and a throw overlap. So throw and a throw overlap also gives you a maximum. So when you join all these points of throw, or crash, which give you a constructive interference, these points are known as anti-node point. When you join them, that gives you a line. That line is known as the anti-node line. Okay, so we have anti-node line. So anti-node line are referring to the line which is joining all the constructive points and will eventually lead to a constructive interference. I mean, what's that? Constructive fringe, which is a bright fringe. Then the points where the crest and a throw meet. Okay, so if it is a crest and a throw, it will give you a minimum, which will lead to a dark fringe. So that particular points are known as node point. Okay, so node point. So the line we can call it as a nodal line. But no need to worry about knowing these terms all. You just understand. Okay. So you have the anti-nodal line and anti-nodal line and a nodal line. So anti-nodal line referring to a constructive points, nodal line referring to the destructive points. Okay. And if you see here, initially, the wave is actually comes from a single source. From a single source, it goes to a single slit, diffracted from the single slit before it goes into a double slit. So why we use this arrangement is in order to produce two, okay, so a coherent source. So it is initially originated from a single source. Then it passes through a single slit to have a diffraction, and then only it passes to a double slit to have two new sources, okay, so which are in phase, a, a, a coherent source. Okay, any question? If you were to further to know more details on this, then you can look for, you can refer to the SPM book, okay, so or you can refer to the IGCSE book under the chapter. But then IGCSE, oh yeah, no, IGCSE you don't go, they don't do interference in detail, no. So you must do SPM. You must look into the SPM book, okay. Or otherwise, A levels book. You look for A levels book, okay. So which covers on in this is in the chapter waves and superposition if it is in A levels. Okay, so next we have observed the general pattern. Okay, so now we are moving on into the formulas. How the formulas has been further derived, and we can use that formulas to solving problems and finding the wavelength. So look at it. Suppose ray 1 and ray 2 coming from a slit arriving at a point P on the, so slit separation D. So you have a slit separation D. Ray 1, ray 2 reaches to a point P. The the distance, the separation, okay, so from the middle, the zero order to the particular point, okay, we take it as Y. Okay, and the distance between the double slit to the screen is taken as D. So the angle, okay, so if you take the center to the particular point where the fringe is being formed on the screen, so then I can measure that angle as theta. This one is 90 degrees. Therefore, my y, which is the opposite divided by adjacent d, that gives us the tangent theta. So fine. So I can find the angle. You will be sort of doing this arrangement of the experiment later. Okay, so when it comes to, I think that is when it comes to experiment 8. Yeah, experiment 8. So your practical experiment next week will follow based on the chapter 3 thermodynamics, which is referring to the specific heat capacity. Okay, so that is next week. So specific heat capacity. So your full report already done. So your practical related to the full report done. So next all are report sheet. Okay. So then after that, there will be slide arrangement. Okay, your practical 5. Okay, so it's supposed to be, it will be brought to as a last order, last practical, because due to some reason the supplier have not, because that is a new experiment. So we have ordered for, is something to, I mean, it is something to study about the diffraction of wave. But then the supplier could not send us the apparatus in time. So therefore, we have some plan B, okay, to bring it later. So we will do the other experiments which can be conduct, okay, so earlier. And this is only for TMP, yeah? Okay, so for your thermodynamics and modern physics. Okay, since we are 2 minutes away, okay, so please look into this. This is more of a deriving. Again, I'll tell you, in the exam, you're not going to derive any formulas, okay? If a specific formula you're going to derive, I will tell you during the lesson. You take note, okay? So if it is not, okay, so we are not going to derive every single formulas. So, but you just understand how it actually works. So, find time, okay, you can just go through this. Okay, there is a process of deriving all this, but final, listen, students, still I have 2 more minutes. Okay, 2 minutes. Don't shut your mode. Okay, 2 minutes. Wait. Okay, so distance of M bright fringe from the center. Students, please. Okay, this was the formula you used for your practical earlier. Okay, so the distance of M bright fringe. Okay, so the process of deriving you can see, but then how this quantities has been related, please just have a look through. Okay, so you can see many process of deriving. Ultimately, we are going to look into that formula has been derived. And of course, these formulas are given in the formula list. Our formula list, I think, compared to all the foundation program in different universities. Okay, so because I have a overview, okay, so most of the foundation, listen, foundation program from the other public universities, I find our formula list, which is the data booklet, it is the most comprehensive. You have all the formulas, okay, which is supposed to be, which is in your syllabus, everything in your formula list. So you don't really need to crack your head to like memorize the formulas, okay? But you must know where to use them, okay? So that's this is one of the most important one. Okay, lambda equals to ax over d. Probably you have also studied that in your during your form 5. Okay, so yeah, this is what we are going to cover tomorrow. This is an important part. Okay, so where you can expect questions in your final. Okay, and also in your quiz. Okay, bye. Thank you. Oh, okay. The to and fro, okay, it is here. it will be along the line of maximum, CF. This is the point. So everywhere, the center part is actually the throw. So if you draw the case, it's something like this now. So it goes like that. So this is a throw. So the other one will meet at the center. Okay. Hmm?
In the previous lesson, it got confusing between. I just didn't understand here why did we have to divide by 2 when it's a destructive, and here destructive is just by.
No.
Here we divide. There we divided.
I don't think so. Destructive, it has to be. Destructive is fine because. Okay. This is one complete cycle, correct? So one complete cycle is equivalent to lambda. And one lambda is equivalent to 2 pi 1. So and a half lambda is equivalent to pi 1. So when the part difference, so we know that for constructive, the part difference has to be lambda. So therefore, it will be 2 pi, 4 pi, because it can be lambda, 2 lambda, 3 lambda, and so on. So this is your path difference. So if I convert this to phase difference, then it has to be in angle. A lambda becomes a 2 pi. A 2 lambda will become 4 pi. 3 lambda becomes 6 pi. That is for constructive. Partial. No. This partial interference. What do you mean by destructive? What is partial? Constructive? Destructive? There is no partial one. There is no they did not mention anything about partial. There's no like a term for partial. Is either constructive or destructive. There will be no partial. Okay, so then go back to the so that is the condition. So this is going to be a constructive. So if it is destructive, then it will be half lambda, 3 over 2 lambda, 5 over 2 lambda. Okay, this is for the.
What is the M? The one M multiplied.
M is the order. So 0 order means M lambda, so M is 0. So you have a M equals to 1. That's the first order. Second order. So if you look at. No. Okay. Yeah. So one wavelength, two wavelength. So that is it. So it is referring to the order. The M is basically 0, 1, 2, 3, 4. It is the order. And eventually that order is also equivalent to 1 lambda, 2 lambda, 3 lambda. Okay, which one? Okay, see, this is constructive interference. So when it's constructive interference, what is the general pattern for constructive to take place? 1 lambda, 2 lambda, 3 lambda, 4 lambda. That's the general pattern. So if your lambda is 600, that is the That's a wavelength. So the constructive will happen at 0 lambda, 1 lambda, 2 lambda, and so on. So we want the three smallest OPD. So, sorry, three smallest OPD between two rays. Okay, so the three smallest OPD means the first OPD is there is no difference, 0 lambda. Second OPD is 1 lambda. uh, uh, First sorry, 0, that's a 0 order. Then the first OPD is 1 lambda, second OPD is 2 lambda. So 0, 1 lambda is 600 nanometer, 2 lambda is 2 times 600. That's all. If it is destructive, then it starts from there is no 0. So for destructive, it starts with half lambda. So half of this, that is the first OPD. Then the next one is 3 over 2 lambda. That is the second OPD. So it goes on. You just put into the formula, that's it. Okay. Yeah.
Sure. I want to ask for the
Yes, what? Practical.
No. Also have some.
Okay, wait.
it equate with tangent theta
Mhm.
with the just now tangent theta equals to y over big T. But how do we confirm that these two angles are the same angle so that it can be equate and get the formula y equals to?
Because this is like when you put 90 degrees, mathematically, okay, these are two parallel lines. Okay, so when these are two parallel lines, and this is theta, okay, just say that this is equivalent to 30, then this will be 60. And this is 60, this has to be 30, right?
You mean this 30?
When I put an example, if I use this is as 30, then this is 90, this is 90. So if this is okay, so this is going to be 60 because this plus this has to be 91. This is already 90. If I take a triangle,
If I see from this angle, this is 30, and then I see
yes.
this is 90,
So this has to be 60.
60.
If this is 60, then 90. So this one go back 60.
Yeah.
We go back to 30.
Okay.
While this was the same, right? The separation distance.
Huh?
Or separation.
Yeah, same. If you take from the center to the center must be same.
But you see another.
Is that a single slit?
Yeah.
Single slit will be different.
What?
Single slit, okay, because it is not two coherent source overlap. So it is just one.
Just one.
One diffract.
Then.
So what will happen is the center one will be wider. So as you go far, okay, so it will become smaller.
So there's no constructive.
Huh?
There's no constructive.
There is constructive, destructive, but the fringe separation, the intensity, okay, so will be single. So it will be like this. So because like center one will be wider, okay, so when you take, okay, so but as it goes further from here to here, so the width will become smaller. So the width forms smaller, okay, so when you take from the peak, okay, to the peak, so this one, so that's why okay, bye. That's why we don't really use fringe separation for this. We will take the distance from the center to that particular order because it is changing.
So also just throw the formula here.
Yes.
Both also can use that.
Which one?
The single slit and double slit.
Yes, both mean what do you mean the formula? So for single slit, we just use for single. So for single slit, we don't use the formula lambda equals to ax over d because the fringe separation is not the same. And usually single slit is not. We don't emphasize much. It's just understand. So we are more emphasized on the.
We always encountered the double slit only.
Yes.
Oh.
That will be what's that? You can say that will be more, it's able to give us a more accurate answer.
Oh, okay.
That's
Okay,
it. Okay,
okay.
good. Mhm.
正在关机中，Shutdown in progress。